Yep.
It's all ours.
Okay. Okay. Thank you. Good morning, so my name is Felipe. I am a postdoctoral fellow at UC Berkeley and Berkeley Laboratory in California. So right now it's 10 a.m. for me, but I assume if you're traveling or if you're already in Brazil, it's the afternoon. So good afternoon to everyone. Um, So yeah, as I was saying before, I want this to be something of a lecture style. So if you have questions at any point, if I say something that's not very clear, just raise your hand. I'm sure somebody will be able to like moderate the questions. Then you can just let me know so I can stop and address at the question.
So are you going to track any questions, or you want us to say that there is some question?
Yeah, I would prefer if somebody
Okay, fine.
help me catch the questions because I might not be able to see the chat, if that's okay.
Sure. Go ahead.
Also, if you want to just unmute and ask the question, I think that should be okay too. Okay. So let me begin by stating a few goals that I think will be good to have in mind to what is that we want with these lectures. And the first of those goals is basically to have uh, a good attachment, a good starting point for particle physics, since the lectures next week are gonna already assume that you have a knowledge or a basic knowledge, working knowledge of particle physics. So I'm gonna give a brief introduction to the standard model and some of the things are gonna be related, obviously, to QCD. So that's gonna be nuclear physics. I'm gonna be making a little bit more emphasis on that, but in some I will talk about the whole standard model. Then the second part is going to be to get some intuition of how do you derive Feynman rules of a given theory. So if you have some Lagrangian, so the Lagrangians are typically functions of fields, and I'm going to describe this in detail later, but for now imagine you have some function and this is what describes your theory. But eventually what you want to do is calculate some kind of quantum mechanical amplitude where you have some initial state, some final state that represents a scattering event. And the easiest way to do these calculations was developed by Feynman, and it's to write these pretty pictures of what could happen quantum mechanically. And these pretty pictures actually represent some number or some equation as a function of the external variables. And in principle, you can derive what type of pictures for a given theory you can write given this Lagrangian function. So we're gonna try to give you the intuition of how this connection is created and how you can take a given Lagrangian and more or less imagine what or take a Lagrangian and know what are the types of diagrams that you can draw for a given process. Um, as you know, these are just 3 lectures. I have 1.5 hours in each of them, and some of the connections here, they can be described in more or less a full course of quantum field theory, which normally takes a semester. So we probably won't have time to go into each of the derivations. I'm sorry about that. But I will try to make all the results that I present as intuitive as possible so that you can get a grasp of what the results should be. Um, and maybe if you want to work through the actual derivation, you should in principle have some idea of what are the steps to get there. And finally, if you have any comments, questions, or suggestions for tomorrow's or the day after tomorrow's lecture, then you can always email me here. This is my Berkeley email. I'll be happy to hear any kind of feedback. So let me begin with then what is particle physics? And uh, maybe easy answer is that particle physics is basically everything. Everything that we see, everything that we interact with, it's technically described by particle physics. So the most basic building block of what we interact with are atoms, right? These atoms are made of a nuclei, and then there's electrons flying around in these nuclei. So here you have protons, neutrons. So all of these things are the interactions can be described by particle physics. And these are also called, also known as nucleons. There was that. And technically, it's everything that we see, but there's a big but here. One of the things that particle physics technically doesn't describe um, is gravity. And the reason for that is that gravity is, as we're gonna see, is very weak compared to the rest of the forces. When I say that the rest of the forces, you might imagine electromagnetism, and then the forces that give rise to radioactivity, etc. But gravity is very, very weak in that sense. So doing experimental particle physics with gravity is still very challenging, and our current models basically are self-consistent to some extent without gravity, so we don't have to add it at the start, and our models are still self-contained. So when I said everything, well, I meant also electromagnetism. So electromagnetic forces are part of particle physics. In their microscopic um, the microscopic representation of electromagnetic forces, so the microscopic explanation of electromagnetic forces can be given by particle physics. And obviously this gives rise to something like chemistry, because the electromagnetic interactions between the electrons in different atoms is what gives rise to molecules, and then, and so on and so forth. Then there is radioactivity. That's the other interaction or phenomenon that can exist. Yeah, so you have radioactivity where, for example, you have a neutron that decays into a proton plus an electron and a neutrino or antineutrino. This is another of the possibilities of how these particles inside the atom can interact. And then you might also be familiar with the fusion and fission nuclear reactions, where you put together nucleons or you break them apart, and they yield a significant amount of energy. But other than these 3 points, so you have these 3 types of interactions, and it's also fair to say that these types of interactions is what allows nucleons to be inside of the nucleus of the atom, because protons, as you might imagine, repel each other as they are all positively charged, but then thanks to the nuclear energy, they stay together. So all of these 3 interactions are basically everything that happens and that can happen in particle physics and that can happen in our universe. So something that we don't take into account are cosmological observations of dark energy or dark matter. But as far as we are concerned, in experiments happening here on Earth, then this is everything that can happen. And particle physics is basically an extension of, or it's building on top of quantum mechanics. So you assume that all of the things in particle physics obey the rules of quantum mechanics. And you also because of the high energies and the small masses that some of these particles can achieve, you also have to take into account the special relativity. So note that it's only special relativity, not general relativity, because we're not taking into account gravity. You can do extensions where you take that into account, but basic or elementary particle physics is just quantum mechanics plus special relativity. And the framework that encompasses these two is typically called quantum field theory. And we will see why field in a second. But for now, it's just useful to know that quantum field theory is the framework that describes particle physics and encompasses quantum mechanics and typically special relativity. And it is what gives rise to these three forces, or can describe these three forces that I wrote here. Okay. Again, if anyone has questions, feel free to chime in. So to describe these three forces, there's something called the standard model. So the standard model of particle physics is the ingredients that go into this framework of quantum field theory that make the description of the forces I just talked about. So there is the matter fields. Again, for now, this is a placeholder, but I will describe them in a second. So this is all the things that give rise to matter. So you have your electrons, you have the neutrinos, you also have muons and taus, which are heavier versions of the electron, and similarly their neutrino counterparts. You also have something called quarks, which are given by 6 different quarks called the up-down, charm, strange, top, and bottom. And typically the way that you split quarks from these other particles is that you make these the leptons. So the leptons are typically particles that don't interact via the nuclear force, and the quarks do interact via the nuclear force. So these quarks are what makes up the nucleons. So the nucleons are made out of quarks, and then you have the leptons that are this. So you see you have what's called as 3 generations of matter fields. Each of them, each generation has 2 quarks and 2 leptons. And the generation order is typically because of how massive they are. So if you go to the right, they have more mass. Okay. And there's also for each of these particles, then there's an antimatter particle. So plus the antimatter fields. Then there's what's called the force carrier. So these are the actual interactions. And we will begin by writing down the gluons. Typically the symbol is G, and these are responsible for the nuclear force. So not all of the matter fields interact with the gluons, only the quarks will interact with the gluons. That's why only the quarks are gonna be the ones making up the nucleons. Then you have your photon, which is the well-known carrier of the electromagnetic field, typically with the gamma symbol. This is responsible for the electromagnetic force. And in this case, the photons interact with quarks and some of the leptons. So all of your quarks have some electric charge, and also the electron, the muons, and the taus are electrically charged. And finally, the third type of interaction is W and C bosons. And they are responsible for what is called the weak force. And this is what allows for radioactive decays, like the one of the neutron. And these W and C bosons can interact with everyone here. So these guys can make an interaction that involves everyone here. That's why in the previous page I have something like neutron goes to proton plus electron plus neutrino. So you see it involves nucleons, which are made out of quarks. It involves the electrically charged lepton, but also the neutron, the neutrino, which is neutrally charged lepton. So these are responsible for these types of interactions because they can basically interact with everyone. And then finally, there is another member of the standard model, which you might be familiar because it was recently discovered, well, recently 10 years ago, which is the scalar field called Higgs. Symbols typically an H. And the property of this field is that it provides mass to the matter fields, or most matter fields. Doesn't provide mass to the neutrinos, but in some extensions of the standard model it could. So I'll talk about that in a second. So it provides mass to most matter fields and also to the W and C bosons. And the mechanism for providing this mass is called as the it's the electroweak spontaneous symmetry breaking. So at this point, I'm not gonna be able to go too much on the explanation of what's happening, but the idea is that the Higgs field has certain properties such that there's a symmetry that's broken, and that gives rise to masses for especially for the WC and bosons and the rest of the matter fields. Okay. So each of these forces has some kind of name once you take into account the framework of quantum field theory. And the name of each of these is quantum electrodynamics for gravity, or for electromagnetic force. Then you have quantum chromodynamics for the strong force. And there's the weak interaction. So these are the common names that you will see in the literature or in classes. You would find that people are talking about QED or QCD, and they are referring to the part of the standard model where the gluons or the photons are the main force playing around. Sometimes you have combinations of QED and QCD where you have interactions with both gluons and photons. And then you also have weak interactions sometimes to be taken into account. Okay, so that's basically all of the ingredients of the standard model. So something that it's important to know is, this is terminology that might be useful, is that the forces in the standard model, so I'm gonna write SM for standard model, in the standard model are gauged. So what is this gauged thing means? So basically, for each of the forces, there's gonna be one gauge internal symmetry. And the name gauge is really just to distinguish it from other types of symmetries. So when you have a force carrier boson, or gauge field, it's gonna couple only to the conserved current of the corresponding or the associated global symmetry. So it's the same symmetry that I said before. So this symmetry here and this symmetry here are the same symmetry, except that in that one case it's referring to a global symmetry, meaning that everywhere in space-time you change the fields in the same way. So let me make a table here. So in the case of well, you have the field, the charge. So each conserved current also implies a conserved charge. So you have the photon field, you have the W and C, you have the gluon. Here you have the electric charge. This is well known. The photon couples to electric charges. And these electric charges are the consequence of a U1 internal symmetry. So that means that there's going to be a symmetry group represented by a face. This is a face. And then I'm going to be able to face all my fields without changing the theory. And all the fields that can be faced, they have an electric charge. So if we go back for a second here, you see that the photon is only going to couple to quarks and these leptons on the top. And that's because all of these particles appear in the Lagrangian in such a way that they can be phased and don't change the theory. Okay. So the second charge here for the W and C is what's called the weak isospin. And this is an SU2 group. So an element of SU2 is a 2x2 complex matrix such that, so this is R, let's say, R dagger is equal to R inverse. So the weak isospin is gonna couple to typically to doublets, so stuff that can transform into one another, so two-dimensional vectors. And in the case of the standard model, each of these two-dimensional vectors corresponds to the two leptons in each of the generations or the two quarks. So the weak interaction can change up to down quarks, electrons to neutrinos, and typically it couples each pair of leptons to within a generation. It can also couple quarks and leptons between different generations, and that's in part of the Higgs mechanism. And finally, we have color. And why is this the color charge? This is SU3. So now your matrix is a 3 by 3 matrix. It still satisfies this property that the Hermitian conjugate is equal to the inverse. And also that the determinant of R is equal to 1. So now the color is gonna couple to three-dimensional vectors typically. And because physicists are very creative, they were like, okay, if we have a three-dimensional vector, we're gonna call each of the components of this vector a different color. So you typically have them be, these three-dimensional objects be red, green, and blue. And then they call these charges the color charges. Has obviously nothing to do with real color, but it's just a nice way to think that there's the three different of them. And in the standard model, as I said, this coupled with quarks, which means that each of the quarks that I told you about has a red version, a green version, and a blue version. So the quarks have a color charge on top of their electric charge. Okay, and that's basically all the things that you need to know in order to build up the standard model. Once I give you all these properties, and if you already knew, uh, if you already know what, how to couple a force carrier with a conserved charge, then you will be able to write down the Lagrangian for the standard model by the things I just told you about. So how to build Lagrangians? Let's go and look at that for a second. So before I move on to the next section, are there any questions about the standard model? Anything that that you guys think you want to know?
Hey,
Yep.
so what about the beyond standard model stuff? Like we have heard a lot, but I didn't know much about that. Can you give us I don't know, 5 minutes, like 2 or 3 lines what it is?
Yeah. Oh, thank you. Yeah. Also, one of the things that I didn't mention is what are the things that the standard model technically can't do, and that's why the beyond the standard model exists. So that's a great question. So it's called the drawbacks of the standard model. So as I said before, there's no gravity. There's no dark matter. And there's no dark energy. And cosmologists will tell you we have observed and we have good evidence to believe that there is dark matter and dark energy in the universe. So if you have a theory that tries to describe everything, you might be missing something if it doesn't have dark matter or dark energy. So it has massless neutrinos. But experimentally, they are massive. How do we know they are massive? Because the only mechanism for a quantum mechanical state to oscillate into one another is if you have different masses oscillations. So we have measured neutrino oscillations from the sun, from reactors, from atmospheric neutrinos, and the only mechanism that allows for the oscillations, so that means that you created a electron neutrino and then you measured a muon neutrino. The only mechanism that allows for these oscillations is that the neutrinos are actually massive. And these are several observations. And so if you want to describe the masses of the neutrinos, you have to add, so you have to add extra terms, extra fields, for example. So these are different possibilities. You can add extra fields, extra interactions, etc. And typically, beyond the standard models are none of them has been proven yet. So you can always extend the standard model in whichever way you want, and then try to make predictions of observations, experimental observations, and then until we find an extension that confirms all of the things that we have been observing experimentally, then we can for sure say this is now part of the standard model and is no longer part of the beyond the standard model. And for example, for dark matter, you can do a similar thing where you can add extra fields to the standard model to describe these dark matter particles. Something that at some point was popular was called, or it's still popular, it's called supersymmetry. So the standard model does not have supersymmetry, but for various reasons, including quantum gravity, so theories of quantum gravity like string theory, they do. So people trying to do quantum gravity, so string theory describes quantum gravity. They would expect that if the standard model is an approximation of string theory, then it should reproduce supersymmetry. But so far we haven't found any evidence of supersymmetry. But once you add, you assume that there's some supersymmetric theory attached to it, or that there is a supersymmetry, you get more fields. So with supersymmetry, SUSY for the friends, supersymmetry also called SUSY. So with SUSY, you get more fields. And then you can look for them in the detectors, and that's part of the searches for beyond the standard model. And the last problem, which is part of the drawback, is not the beyond the standard model. So each extra fields basically means beyond the standard model physics. So if you add anything else to all the fields that I just described, then you're talking about beyond the standard model physics. And then the last thing is that strong interactions are hard to predict. So what does that mean? QED, for example, has a coupling. So the coupling is almost equal to 1 over 137. Which means that you can assume that things interact once, and then the second time they interact, it's going to be suppressed by a factor 1 over 137. The third time they interact, it's going to suppress by another factor 137. So a good approximation is to take that they only interact once, and then that gives you already a good description of the experimental data. But then in QCD, the coupling, the strong coupling, is basically 1. And that means that you can assume that two quarks interact once, but then if the two quarks interacted twice, that gives you an amplitude, these quantum mechanical amplitudes, that is of the same order of magnitude. And then if they interact 3 times, it's still the same order of magnitude, or 4 times, still the same order of magnitude. So there's no easy way to make a good approximation based on the amount of times particles interact with each other. And you have to circumvent this with different types of techniques. You have to do what's called effective field theories. And maybe I should just mention really quick what an effective field theory. Well, let me first say what the field theories are, and then if I have time, I will mention what effective field theories are. Okay, so this is part of kind of the drawbacks, is that there's a lot of things it cannot describe, and then you're trying to use beyond the standard model to describe the extra things. On top of this, there are specific measurements that you can imagine, like very specific and properties of individual particles that can be predicted from the standard model. And then if the prediction fails, then you might expect that there's some extra field from beyond the standard model, that is changing that property of that particle. But this is basically a summary of what beyond the standard model is trying to do. And then the extra drawback is, so this beyond the standard model are kind of these 3 points. And then this last point is just an extra drawback about the standard model. Okay? Thank you for the question. Okay, so let me talk about fields. So in classical mechanics, you have typically a description of your system in terms of a position and a momentum state. And then if we want to quantize it, if we want to go to the quantum world, then your observables or become operators. So now you have that the position and the momentum are operators in a Hilbert space, and the states are described by vectors in this Hilbert space, right? So that's how we go from classical to quantum mechanics. And these are when you have a finite number of degrees of freedom. So what happens if now I assume I have an infinite number of degrees of freedom? And in classical mechanics, a good example is the electromagnetic fields. So the electric and magnetic fields. Magnetic that obey, Maxwell equations. Now, the degrees of freedom here are infinite in the sense that for each point in space-time, you have a vector. In this case, the electric and magnetic fields are vectors, but you can imagine a temperature field corresponds to only one number. So that's not the important part. The important part is that for each position in space-time, there is there are degrees of freedom. So if we take into account all of space-time, then we will have an infinite amount of degrees of freedom. And you can take the same idea of the quantization procedure and have fields. So phi will represent a field over space-time. So I'm gonna typically use phi and psi to represent quantized fields. So you can imagine there's a hat here, similar to in X and P, where now phi and psi are operators that depend on a space-time. And you still have states that will describe, you know, the literally or you still have vectors in a Hilbert space that describe states of the system. So this is what's called this quantization of fields. This is what's called quantum field theory. Okay. And the easiest example that you can imagine of a quantum field theory or of a field theory. So let's begin with just a field theory. Is a Lagrangian example. You know, it's something that depends on X, where you have the derivative in time of these fields. And then let me just write this as example. You have a term that depends on the gradient squared of the field. Again, this is a function of X. And what is typically known as a mass term, phi of X. Okay. So this is how you typically define field theory with a Lagrangian. Because it makes it easier, I'm going to use what's called the Einstein summation convention and write derivatives as these. So you have the derivative of phi, and times the derivative of phi minus 1/2 m squared. Oh, the field should be squared here. Sorry. Okay. Is anyone unfamiliar with this type of derivative index notation? I feel like most of you might already seen this. Okay. And so the action is basically the integral over spacetime of this Lagrangian of X, which if you are very strict, this is technically a Lagrangian density because it is it's not only the integral over t, but also the integral over spacetime. So that means that this is basically the density of the Lagrangian over space. So if you have an action, you can derive. So this is still classical. If you have an action, you can derive equations of motion through the Euler-Lagrange equations. that in the case of a Lagrangian density are given by this derivative of the Lagrangian. So you take the derivative of the Lagrangian with respect to any derivative of the fields, and that is equal to the derivative of the Lagrangian with respect to the field. So that means that you have to treat your Lagrangian as a function of phi and the derivative of phi. In this case, the Euler-Lagrange equations are going to give us derivative squared of phi plus m squared equals 0. Okay, so this is my equation of motion for this example. And in order to solve this equation of motion, then you can propose an ansatz and say, well, this looks like a second on the order differential equation. So maybe I can just propose some form. So I propose some function of p, and then this exponential that depends on p and x, complex exponential. So if we insert our ansatz back into the equations of motion, we will obtain something like minus p squared or minus pm plus m squared f of p equals 0. And now f of p can be whatever function we want, as long as this p satisfies pm equals m squared, right? And this is also written as sometimes p squared equals m squared, which is the Einstein's. So you can imagine that if we make a correspondence between this p vector and then energy and spatial momentum, then this will correspond to the relativistic dispersion relation. Okay, so from the Lagrangian, of these phi fields, we arrive to a field that satisfies the relativistic dispersion relation. So that's typically the way that you use classical field theory. And as we will see tomorrow, we will take the same ideas, but now quantize the field, impose commutation relations. So we will have to quantize the field. And that means imposing commutation relations. And we will see where does that take us. In the sense of what kind of theory we get out of that. Okay. But I'm gonna go deeper into that tomorrow. Before that, I wanted to say something about nuclear physics and the quarks and the nucleons. So before I change subjects, are there any questions about classical field theory? Okay. So tomorrow we'll see more about that in the quantization. Okay. So you remember this type of, so I have the up and down, charming, strange, the top and bottom quarks in the standard model. You may wonder, well, you said that these compose the nucleons. But you might be wondering, like, how? Or yeah, basically how. And the answer to this question is we're still working on it. And it has to do with the fact that the coupling is strong. It's basically of order 1. So you cannot really do perturbation theory to calculate the interactions in between quarks with one another. And furthermore, even if you have just the gluon, we still believe this will create composite particles. We have numerical evidence for this. And you can create some simplified models of the standard model, and then you can reach this conclusion. But we don't know how, full or not with the full standard model analytic solution. And if you guys know how, you can win $1 million from the Millennium Prize. So there is a prize that is waiting out there for someone who can describe how gluons on its own can actually create composite particles by using a full analytic solution. But anyhow, so in case you're wondering how to get some easy money, that's probably not the best route, but maybe some of you might find a good way to do it. In the meantime, something that we know is that phenomenologically, only color neutral particles are observed. So what does this mean? So this is equivalent to, say, charge nuclear neutral, but with the color charge. And the equivalent thing in QED would be as if we could only see bound state of electrons and protons, so like the hydrogen atom, but we were never able to observe an electron or a proton independent from each other. The thing is, you can experimentally, separate electrons from protons. The energies to do this is actually quite small. Well, relative terms, 13 electron volts. So it's easy to split them apart. But then the protons themselves are states of quarks. So 3 quarks would make something like a proton. But no one has seen, or we don't expect, or we haven't no observation of a single quark. And this property is called confinement. So I might write this here. So this is the property of confinement that we haven't observed any isolated quarks, because isolated quarks would have charge, color charge. Any isolated quark would either be red, green, or blue. But we have only seen quarks binding together and forming nucleons. And in particular, a color charge can combine in 2 different ways to make it color neutral. So there is a quark-antiquark combination. So you can imagine quarks have red charge, blue charge, green charge, and antiquarks have anti-red, anti-blue, anti-green. So a blue and an anti-blue quark, they cancel their color charges and they can form a colorless state from a quark-antiquark. Obviously, if you have red plus anti-blue, that's not good. But if you have red plus anti-red, then that's fine. And the other possibility, that's what happens inside of of nucleons, is that you can have 3 quarks. So you can have a Q, 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 or anti-Q, 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 and these will form colorless combinations. And this has to do with the symmetry group SU3, where you can form, you can take 3 different elements of this SU3 group and form something that doesn't transform or transform trivially under the group. So this 3 quark part is harder to explain intuitively, but it has to do with the symmetry group of color. Okay, so it seems that if there's confinement, if we cannot do perturbative expansions, then we cannot know too many things about the quark, about the protons and neutrons a priori. But then there is one property that at least allows us to have some knowledge of nucleons, and is that the mass differences between quarks between U, D, and S are small. So what do I mean with small? Well, if I have mass of the U quark minus mass of the D quark, this is very small compared with what's called lambda QCD, where this is basically the scale of confinement. So where confinement takes over. And similarly, if we just assume mu is proportional to md, this is equal to m light L, then ml minus ms is smaller than lambda QCD. So notice that here this is way smaller, and here is just smaller. So in the eyes of the interactions between gluons, then the difference of quarks, of the mass of the quarks in up and down quarks is very, very small. And why does that matter? Well, if there's mass degeneracy, meaning if the masses are the same, then this implies asymmetry. So apart from the gauge symmetries, if you have the mass of the quarks being the same, you gain an extra symmetry. So for that, I'm gonna show that I'm gonna write the Lagrangian of the up and down quarks. So this is gonna be the Lagrangian of up and down. So notice that this Lagrangian is very different. So first, the first difference is that this D slash represents Fermi matrix, encodes the properties of spin half particles. And now you have the anti-down and the down, the anti-up and the up, the anti-down and the down that appear in the Lagrangian. You have a mass term for each of them. So the details I'm not gonna emphasize too much, but the important part is that if mu is equal to ml equal to md, I can rewrite this Lagrangian as q d some unit matrix minus ml. So I don't need the unit matrix because so anyway the unity. But now q represents a two-dimensional vector, up and down. So these two Lagrangians are the same if the masses are the same, right? If the masses are the same. And note that if I take this new Q field and I create a new Q field that is equal to RQ, where R is an element of SU2. So this is different from weak SU2. Just happens to be the same group, but nothing to do with the weak interactions. So if I take this, then the new Lagrangian becomes RQ bar D minus ML RQ. So this bar is basically a Hermitian conjugate. So you get Hermitian conjugate for the matrix R. This matrix R commutes because these are one-dimensional in this space. And then we said that this is equal to unity. Because an SU2 matrix, R dagger is equal to R inverse. So L prime is going to be equal to L. And this is what I mean whenever I say symmetry. A transformation that leaves the Lagrangian invariant. That means if the Lagrangian is invariant, the equation of motions, the equation of motions are going to stay the same, and the equation of motions to stay the same. So sorry, Bruna, do you wanna?
I have a question.
Yes.
I saw in a book a few weeks ago about neutrons and protons, and when we have these two together, they have very similar mass. They're
Yeah.
not identical because of charge.
Yeah.
Can we apply the same treatment that we gave here to the how to write the Lagrangian for the two of them? Because I know we can build an isospin space where neutrons and protons, they are almost the same. We can go from one to another with using a rotation in this isospin space. Can we do something similar when writing the Lagrangian?
Yeah, and basically you just spoiled the results that I was gonna get into. But yeah, that's gonna
Okay.
be basically the idea that
Okay.
because protons and neutrons are gonna be made out of quarks, they will inherit the symmetries that they have, that the quarks themselves have.
Mm-hmm.
And I will give you an idea of why the proton and neutron are in this doublet in just a second.
Mm-hmm.
Yeah,
Thank you.
great question. So that's what a symmetry is. So it's a nice way to also introduce a symmetry. And yes, as Bruna said, if the mass of the U and the down are similar, then you have an SU2 symmetry, and this is called isospin symmetry. Now, if you assume the U, the down, and the strange have the same mass, then you have what is known as SU3 flavor symmetry. The symmetry is not as good because the mass of the U and mass of the D are known to be are known to be of the order of a few GeV, a few MeV, whereas the mass of the strange is of the order of 100 MeV. So obviously these are not great approximations, but because the confinement scale is a few hundred MeV, then the strange and the up and down quarks, they have similar masses, or the difference is small with respect to this lambda QCD. So, as we said, there's an isospin symmetry. So, let me just go to a new page. So in isospin, Q and Q bar are SU2 doublets. So this is a terminology similar to SU2 is also the symmetry that represents rotational invariance. And then when you have spin half particles, then you have them as doublets. Here SU2 represents an internal rotation, mixing together up and down quarks. But since it's the same group, then you can use the same notation. So that means that a Q bar creates 1/2 cross 1/2, which in group theory, in SU2, that means that you have a singlet and a triplet. The singlet has U bar plus DT bar, and the types of particles you can create in this way are called mesons. So the U bar plus DD bar is what would form an eta meson. And then the triplet, you can have UU bar, sorry, UD bar, UU bar minus DD bar, and D bar U. And this is what's called the pions. So pi plus, pi 0, and pi minus. Then when you have 3 quarks, then you have 3 doublets that combine together in flavor space. So this is in UD space. And this creates 2 doublets and 1 quadruplet. The quadruplet, this way of creating this way of mixing quarks, you get what's called baryons. And the quadruplet is the delta baryons, delta minus, delta 0, delta plus, and delta plus plus. And then from the doublets, there's only one allowed combination for the ground state. And that is the N and P. So mixing together these 3 quarks, you get an isospin doublet. Which is the nucleon and the proton. And as Brunan pointed out, you can now formulate a theory that only involves the nucleon and the proton. And as long as isospin or the mass of the U and D quarks are very similar, then you can assume that the properties of the neutron and proton are going to be very similar to each other. So that's with SU2. But technically the more famous one, and the one that is used to classify particles, is typically SU3 flavor symmetry. So in SU3, Q is going to be a vector of up, down, and strange. So it's a triplet in flavor space. And Q bar is an anti-triplet. So to form mesons, then we're going to have Q bar, it's going to be triplet times an anti-triplet. So this is SU3 notation. So the symbols here are similar because this is still group theory, but then the particulars of each symbol of each of the numbers is different because now this is a different group. And in SU3, the combination of a triplet and an anti-triplet gives you an octet and a singlet. Octet and singlet. So this octet is typically represented, and you might see this a lot, as this hexagon, where you have the different combinations of quarks, ds bar, us bar, d bar u, u bar u, d bar d, u bar d, s u, and s. So if you see this kind of an hexagon, and the way to accommodate this is that if you notice this is what strangeness 1. So something funny about strangeness, or the convention of how to tell strangeness, is the amount of strangeness is the same sign as the electric charge of the quark. And since the electric charge of a strange quark is -1/3, and an anti-strange has positive strangeness, and a strange will have negative strangeness. So to match the sign of the electric charge, so QS. And then this line in the middle is strangeness 0. And then each of the particles in this octet has a name. So I'm just gonna rewrite the octet, but with the names of the particles. So you have the K0, the K plus, the pi minus. Then in the center you have two possible linear combinations. One of them is the pi 0, the other one is the eta. You have pi plus, and technically you also can have S bar here. The K minus and the K bar 0. So writing it this way, you can also notice that these diagonals correspond to charge, electric charge 1, electric charge 0, and electric charge -1. And then there is the singlet, which is the eta prime. That will correspond to the linear combination of the symmetric linear combination of up, down, down, plus S, S. So there's this linear combination, and then there's two linear combinations left. And that's what forms the pi 0 and the eta. So these are the octet of quarks. And then for baryons, you have 3 cross 3 cross 3. So the quark, quark, quark construction. And in this case, you have a decouplet, 2 octets, and a singlet. So the decouplet is what forms the delta baryons again. So this is the extension of the quartet to SU3. But now you have more baryons here. So what's called the sigma sigma star minus, sigma star 0, sigma star plus. These guys are called cascade star minus and cascade star 0. And then the omega. And similar than before, you have strangeness 0, strangeness -1. So the strangeness goes down. Strangeness -2, strangeness -3. So this basically means that the omega is S. Again, there's one combination for the ground state, and this forms the nucleon, the proton, and then what's called the sigma minus, sigma 0, sigma, it should be plus, sigma plus, cascade minus, and cascade 0. And there's a lambda here. Again, you have strangeness 0, strangeness 1, strangeness 2. Now, since SU2 is a better symmetry, and so SU2 is more accurate, more isospin. Then the mass of the proton, mass of the neutron, is the difference between these masses is also the order of few MeV. And then in SU3, the difference in mass between the proton and, for example, the sigma is of a few hundred MeV. So this is expected because of how similar the masses of the strange and the down versus the masses of the down and the up are. But this is still very useful to classify the different types of baryons and mesons that you will observe experimentally. Here I'm just showing you the ground state of the quarks. You can imagine that if you have the quarks in some excited state, you can also form baryons and mesons, and they have also different names. But for now, I'm just gonna show you the construction of the ground states. You can imagine a similar construction for the vector mesons or for the scalar mesons, etc. Okay. So I just want to finish with an example of its isospin symmetry. In a reaction. So let's say we have 3 reactions, so proton-proton fusion into a deuterium plus a pi plus. So D is Pn bound state, and the isospin D is equal to 0. Okay, so you have proton-proton fusion. Then you can imagine you have proton, neutron going into deuteron plus pi 0, and finally neutron, neutron going into deuteron plus pi minus. So all the experimental combinations that you can imagine you can form. So this is going to be 1, 2, and 3. So the initial state in 1 is gonna be the isospin doublet with Iseta one half. So as I said, proton and neutron are an isospin doublet. And the pions are in an isospin triplet. If you know your Clebsch-Gordons, then you know that this is just 1-1. Then the initial state then the final state in 1 is just a 1-1. So the pion, this is the pion, plus cross 0-0, which is the deuteron. This is just 1-1. And you can do a similar exercise for initial state 2, which is gonna be 1/2, 1/2, 1/2, minus 1/2. And the Clebsch-Gordons are gonna be 1/√2, 0, 0, plus 1/√2, 1, 0. The final state in 2 is very easy because it's just the deuteron and the pion, which is gonna be a 1, 1, 0. Initial state 3 is 1/2, minus 1/2, 1/2, minus 1/2. This is just 1 minus 1. And the final state in 3 is just 1 minus 1. So if you take the final state to initial state matrix element, so you will find that there's a ratio between the process 1, the process 2, and the process 3 of 1 over square root of 2 and 1. And the probability is the square of this ratio, of the square of the matrix element. So you're gonna have this. So dynamically, you expect that the second process only happens half of the time. So this is a dynamic constraint. And the other two are gonna happen mostly equal at equal rates. So if you're very curious as a homework, you can go and look around what are the rates of each of these processes and see if they indeed have 1, 1/2, and 1 as predicted from isospin. This is in part what isospin allows you to predict. And with that, if there are questions, please go ahead. But that's all the material I have for today. And I'll be happy to see you guys tomorrow.
We know that the SO3 symmetry is less accurate, so can we estimate how much error introduced this symmetry?
We can try. We can try to do that with an effective field theory. And I guess I didn't have time to talk about the effective field theories today. So I'll make a note to talk about that tomorrow. So you can try to make a prediction of what the corrections are going to be for your inaccurate or broken symmetry. So you're gonna have, again, has to do with how to deal with broken symmetries or approximate symmetries in quantum field theory. And it's gonna work on certain regimes. That's the conclusion. Things like masses, which are, static properties of particles, they might work better than dynamic processes like the collision of particles. But there's even static properties like um, the the anomalous magnetic moment, where you can try to predict the correction and then you still have a poor prediction based on the approximate symmetry. But that's more of a dynamical detail. So it has to do with each of the theories and what the dynamical properties of each effective theory is.
Okay, thank you very much.
Yep. Thanks for the question.
All right, Felipe, it seems there is no further question. Then
Felipe?
Yep.
there is one way.
Thank you. Felipe, first I would like to thanks for the lecture. I have another question. When you are mentioning about the Millennium Prize, was talking about the possibility of gluon create composite particle.
Yep.
How the this this creation of composite particle related with the gap mass in the Millennium Prize?
Yeah. So the Millennium Prize, the way it's formulated is that there is a mass gap. So the way that, if you go to the webpage, you will see that the formulation of the question is show that there's a mass gap in the theory of Young-Mills, which the theory of Young-Mills is basically QCD without the quarks. And part of the idea is that individual gluons in the theory are massless. So if you're going to have a mass gap, they have to be a composite particle of gluons. Because individual gluons are massless. And furthermore, you have to have confinement where the gluons cannot be by themselves. So that these two things logically are connected, it's a little bit, it's not proven. That's part of the Millennium Prize in a sense. But this is what we expect from phenomenological reasons. So in other words, if you can make that connection yourself, how the composite particles give rise to the mass gap, that's probably part of the answer. But that's just the best guess that we have right now.
Okay, thank you.
I have another question. When
ahead.
you talk about the mass degeneracy, the Lagrangian only have terms of up quarks and down quarks. Why you don't have a mixed term? Is that because you will not have a colorless combination? I don't understand that part precisely. Or you broke the isospin symmetry. I don't know. Yes, that Lagrangian.
Yeah, let me see. Here. So you mean a combined term, something like U bar, some M term mixed. So something like this?
Something like that. Yeah.
Yeah, I mean that's a fair question. A problem with this term is that um, I mean it violates isospin symmetry, but also you would have a term that goes like this. So the equations of motion now are gonna be coupled. Forgetting about the masses, just the derivative, which it gives rise to the dynamic equations. So the equation of motions are gonna be coupled between U and D. And this is no longer gonna be a free theory.
Oh yeah.
So
You
you can always
are
imagine,
think- you are
can
thinking about the free part of the theory, right?
yeah, yeah,
Okay.
exactly.
Okay, thanks.
So we're beginning with a
I-
free theory, and that's why.
Sorry
Thanks.
to interrupt. Hello,
Have-
Felipe, by
have-
the way.
You have further insights, Sebastian?
Yes,
Go ahead.
I think it will be a free theory.
But
But
you
it-
just have to rotate it around? Or
Yes, it's just that those two Lagrangians, I believe I forgot from my studies, but I think they are equivalent.
yeah, I can imagine
to-
it's gonna be
You
a
just
rotation.
have to redefine the fields. And those two Lagrangians describe the same physics.
Yeah, that makes sense. That the only reason why you wouldn't be able to rotate is if there's another term in the Lagrangian that will change and not stay the same with this rotation. But then in the case of the free fields, I think Sebastian is right that you can always find a rotation so that you get at the end this Lagrangian.
Or you can
Yeah.
see that the terms like U derivative D can be, as far as I remember, written as full derivatives.
Mm. Yeah, so you will give nothing on the Euler-Lagrange equation in the end of the day.
Yeah, but any free field theory with many fields is essentially a quadratic form that can be diagonalized, which essentially means redefinition of fields.
Yeah.
All such theories are equivalent, probably up to some subtleties.
Mm-hmm.
Yeah, that makes sense.
Okay, thanks.
All right. Thank you, Felipe. So we meet tomorrow again at the same time.
Yep.
So if you can send these slides to us, we can post them on the
Yeah,
on the
on the
website.
website.
Okay.
Yeah, I can do that.
Okay, thank you.
Okay.